Hello, everyone, and welcome to our Logic Technology Roundtable in cooperation with Tuxera on techniques to safeguard critical data for IoT. My name is Gevorg Melikdjanjan, and at Logic Technology, I am responsible for Tuxera's flash file system and flash management solutions, and I will be today's moderator. Our guest for the roundtable is Thom Denholm, Technical Product Manager at Tuxera. Welcome, Thom. So before we get started, I would like to go over a few items so that you know how to participate in today's event. You will have the opportunity to submit text questions by typing your questions into the chat box. You may send in questions at any time during the presentation. We will collect these questions and address them during our Q&A session at the end of today's talk. I would also like to kindly ask everyone to mute their mic and switch off the camera in order to have proper bandwidth. Thank you. So in today's growing number of autonomous systems, preserving decision quality data is becoming all the more imperative. Through different use cases, environmental circumstances, or simply when devices become older, problems may come to the surface that were not visible before. This is not acceptable for devices containing sensitive data. Therefore, through the course of this roundtable, we hope to learn more about the...
É sobre o PSM do módulo. Tu nunca fizeste nenhum teste do PSM
I'm sorry.
do módulo.
I would like to, João Batista, I would like to kindly ask you to mute your mic, please.
Thank you.
So where was I? Therefore, through the course of this roundtable, we hope to learn more about the techniques on how to protect critical systems from data corruption in embedded devices where power loss may occur. So let's start our conversation, Thom. What do you think is the most important technique?
Thanks, Gevorg. I've been working with file systems since 2000, specifically with Tuxera, Datalyte before that, DOS system calls before that. So in my experience, the number one cause of loss of data is overwriting that data.
Seems simple, but I'm sure there's more to it.
Yeah, of course. So in order to modify a file, you have to overwrite the existing data. If the power's lost, you really have no idea what state that data block is in, the one that you were modifying. Did you get all of the data to the media, or some of it, or none of it? You really have to consider that file corrupted at that point, or at least it needs to be examined by either a person or a program that created it. Examination of potentially corrupted data isn't in the normal job description.
So what if you don't modify any files?
Yeah, not modifying files, changing the way you use the file system is an option for that user data, but really it's no guarantee overall. For the use case of appending to a file, there's still a modification happening. This time it's not completely under your control because it's to the file metadata. Okay, that's the data that points at the size of the file, the date and time, all that. So the same problem occurs. If the power is interrupted while updating that block, what next? Did it get done? Is it partial? Is it not done at all? You have to rely on the file system to decide what's a good file and what isn't. And that's not usually part of the design. So if the file's in a subfolder, then there's metadata for that subfolder, and so on, and so on. These are single block updates at the metadata level, so these can be guaranteed with what is known as an atomic operation at the media level. So with an atomic operation, either the entire block is written or none of it is written, which is a much more predictable solution.
Okay, so basically an atomic block update and no override solves the problem.
Yeah, in a way. Change the way you work with the file system, choose the right media with the atomic updates, that can help. Did you also provide the application? Is that application written the way you expect it to be? Is there some sort of a direction to anybody who does provide applications in today's Android type world where you can download applications? So there's another way though, and that really comes back to this first predictable solution, and that's transaction points. A simple way to describe a transaction point is like a database. When you perform a series of operations on the database that are designed to go together, they either all happen or none of them do. The entire thing is one atomic operation, like we were talking about earlier. A file system can perform a series of operations and then issue a transaction point. Once that transaction point is successful, all the operations happen. If the power's lost, then none of the operations have occurred. To do this, the file system has to have the transaction points built in, and it cannot overwrite the existing data. That data is known good.
Okay. So speaking of power loss scenarios, perhaps an interesting question for the listeners. What kind of measures have been taken by your development team in order to protect the data stored in your applications in the case of a sudden power loss? So you could be using a non-volatile memory or a battery backup system, or maybe some other solution. Please type in your comments in the chat box and we will address them at the end of the talk. So Thom, to come back to your point about the transaction point settings. So if I understand it correctly, this is the Reliance family of file systems, right?
That's right. The Reliance family uses a master block and two meta roots to track the state of which system is the working state and which is the known good state. There's a few sectors involved here, and they take up a lot less space than, say, a Linux file system journal. And yet it provides a lot more capability. Let me demonstrate with three common operations. We'll collect them into one atomic operation using a transaction point when complete. So once we perform the operations, we do the transaction point, we end up with a successful state. The file that was erased is erased. The modified file, notice we didn't modify the block in place. We created a new block for that. And then we created a new file. If the power was lost, if something happened, the system crashed or something like that, it would revert to that previous state. Okay, so this is, again, this design fits well with NAND flash memory also, because the NAND, you can't overwrite the blocks. You cannot overwrite NAND block data. So the other big advantage here is that no check disk or journal scan or rebuild or anything like that is necessary.
Okay. Thank you. I'd like to come back to the list of techniques. So what is a copy on write?
Right. So like we just mentioned with NAND, let me go a little bit more into NAND. That although this is just a very brief introduction, a full discussion of NAND could take the rest of our time here today. NAND media is an abstract view here of NAND media. So there's two important objects, the write page and the erase block. The minimum size you can erase is one erase block. The minimum size you can write is one write page. Okay, the write page cannot be overwritten or appended to. If you want to update this page, even if it's only partially filled, you need to create a new one. And then you'll mark the original one as obsolete. This is known as copy on write. So file systems which are copy on write are a great match with NAND flash-based media, which is inherently copy on write. Okay,
and this is handled by the firmware.
Yeah, that's right. Firmware for managed flash memory like eMMC, UFS, SD, SSD. There's also raw NAND flash, and there's software, a software controller, if you will, that handles this. We write it. It's called FlashFX-Terra.
Okay, and it takes care of everything, basically.
Well, mostly, not quite everything. So FlashFX-Terra takes care of the wear leveling, the bad block management, and customization of things like the block size and the error handling. Error correction has to be handled by a controller because the math gets really intensive at that level. Another thing that we can't handle is the write amplification. So the file system, if it writes a small amount of data to one of these write pages, you end up with atrocious write amplification because, again, you can't append to it. You can't continue. One of the most important considerations of flash media is it doesn't last forever. Unlike other media, it has a very predictable lifetime. The correctable bit errors grow over time. The media uses replacement blocks and then erases those to get some life back, but you don't ever get more than the manufacturer recommended. In this case, let's say 10,000 cycles. After that, the bit errors become too frequent to be corrected. So really, lifetime comes back to how frequently you write and how many of those writes are complete versus partial. To put it in another way, the goal is low write amplification for the highest lifetime. All Tuxera file systems are designed for minimal write amplification, and we really do utilize flash-friendly operation at all levels.
Okay. Do you have an interesting example for a use case where you have extended the lifetime of a device?
Sure. So we worked with a customer that made power meters. Okay, they were running Linux in this case, and they were looking at Linux file systems and Linux options. The media was eMMC, if I recall correctly. They had an advanced lifetime simulation, and the default Linux solution that they were using, ext4, got them roughly 18 years according to their measurements and estimations. They needed a 22 in their 20, excuse me, in their requirements. This had to be 20. So they were looking at ways they could customize that, but they reached out to us and said, "What have you got?" So we shared our file system with them, and that showed up to be 22 years right out of the box. So already it's a design which has a much lower write amplification than the default ext4, more flash friendly too. So they were happy with that, but we stopped. We said, let's go a little further, right? We brought the support team in. We did some customization to match their needs for the data to what we could provide, customizing the size of a transaction point, how frequently they're written. In the end, we had a result of more than 30 years of lifetime on their advanced lifetime simulation. And remember, their original goal was 20. So that's way above the standard there.
Yeah, okay. Thanks for that example. So let's go back to the wear-related failures. I think this is where you left off.
Yeah. So this all comes back to complete system integration, really. Understanding what the hardware does, what it's capable of, including the write amplification, but also including the lifetime, and balancing the software match to that is really key, really critical here. Another example, the folks at Tesla designed a solution they thought would last 10 years. They used a standard SoC that met their needs. There was a recent report, we've written a blog post about it, where they demonstrated in this report that they didn't really have a complete picture of how frequently the OS and the applications would write their log data. They wrote several small packets. Those small packets were flushed immediately. So they compounded the problem by creating a large write amplification. They tried some short-term solutions like generating less log data and reducing the need to flush, but the damage is done. The flash media on a Model S with 70% of usable lifetime used is really heavily worn. There's basically 3 years left of the predicted lifetime at that point. And really, there's not much you can do to make that last 8 years, no matter what the software does. The later designs and the warranty repairs incorporated a larger part. The report referred to this as terabytes written was the measurement. So basically a calculation of the number of writes versus the size, and multiplied by the size of the device. And then that they also added a better profile for data logging operations. So really, that comes back to what we were talking about here. This is a complete solution. They examined what the hardware could do, what the software could do, and matched them up.
So what are some other integration points?
I think testing is a major factor in that complete solution. The design should take those kind of tests into account. One example of that is the process direction of automotive spice, which we use for our Reliance Edge Assure product. That provides complete traceability from the design all the way down to individual lines of code, which have individual lines tested. Every line is tested. So again, working closely with the board or SoC manufacturer is key here. Having great testing is key. These all come back to other parts of the Logic solution. Logic provides boards, has many partners who provide SoCs. We also partnership with LDRA, so some of that validation of that design can be handled at that level. All should be really part of that complete solution.
Okay, then I think the last item is security.
Indeed. Understanding the impact of security requirements. We've been talking about safeguarding your critical data, right? And really all data is critical to someone. I mean, you wouldn't write it out if it wasn't important, right? Secure data, though, that's an entirely different matter. Now we get into legal requirements and jurisdictions, and that data really needs to be managed properly. At the simple level, that could be encryption, but encryption is not a complete solution. There's no lasting protection through obscurity.
When you talk about encryption, what level of encryption do the Reliance file systems family provide?
So currently we have an encryption plugin. You can connect at that level. On Linux, we work with encryption at two different layers, the DM crypt, which is an entire block device encryption. And we, with our Flash Xterra solution, we can provide that on raw flash media, which the flash file systems on Linux cannot. At the file system layer, the Android folks over at Google have been driving FSCrypt, file system encryption. You can encrypt separate folders and separate files even within the file system with different encryptions. So we've added that to Reliance Nitro, although it seems like every other Linux kernel that comes out, they update that and change that. So we've had to keep up with those Linux kernels in our product. But ultimately, yeah, we're one of the 5 or 6 different file systems on Linux that support FSCrypt today.
Okay, and the encryption, is that only at directory level?
As I understand it, the directories are the subfolders. And so when you encrypt that folder, you encrypt every file within that folder. But then there's a tree operation there as well. So you could encrypt within the tree. Perhaps you could have different encryptions. Quite a few options, really.
And this is only available for Linux OS.
Yes, the FSCrypt application, again, that we connect to as a library, really, and that's on Linux. That's provided on Linux. The Reliance codebase is the same codebase for other RTOS environments. So, like Wind River VxWorks, for instance, when they add an encryption library, and I'm sure they will soon, it would not take much to just adapt our calls to that new library. In fact, Wind River folks provide Linux as well, so it seems very likely that they'll have a similar solution in-house. Another option would be hardware level. A lot of these boards and SoCs are coming out with a hardware encryption chip, which handles that. You need some sort of a device driver to talk to that chip to be able to, say, encrypt or decrypt. And then those encrypt and decrypt functions could be then connected back to the file system. Because again, we have a plug-in layer where that's available.
Okay. So speaking of ports, what if you implement the file system into a Linux OS, and after a while you want to switch to a different operating system, but you still want to use the Reliance file system? How does that work?
Well, so the core is the same across all ports that we support, and including an RTOS port where we can port to any RTOS you're interested in. So at the very base level, you'd be very used to working with the same file system. The media on media storage is also identical. So they use the same on media format. So if you had a design on Linux and decided you wanted to switch to VxWorks, I keep using them as an example, but they're newer than Windows CE, aren't they? So you could do that. You wouldn't have to change much. You'd change the driver level because obviously it plugs into the OS at a different level, but the media wouldn't change. A related solution would be, say, a hypervisor, or some sort of shared storage solution where you had multiple OSs in your design working with one media or the same media. So you could have a Linux design, you could have a Green Hills Integrity design, all working off the same media, and because they share that same common media format, that would work just fine. Before that, the only other option you'd have to share storage between two different OSs would be a common format, like, say, exFAT. exFAT is a good solution. We also sell that, but it doesn't provide the data integrity that the Reliance family of file systems provides.
Okay, so with a hypervisor, can you then still use the FlashFX in order to communicate with the Flash?
Sure, absolutely. Probably what you would end up is one thread or one OS within the hypervisor would handle all the communications with the Flash. The Flash media really requires one controller. You tend to issue a write and then do a wait for the write to complete. You can't really have a second OS waiting for that same write. But that would work just fine at that level.
Okay. Thank you, Thom. I think we left off at the part of security where the data has to be securely removed.
We did, and in fact, that's something I'm talking about later today, actually, at the conference. If you have a conference pass and you'd like to attend, this is the session I'm hosting at 1400. If this is something that you don't have a conference pass, but you're still interested in this topic, reach out to us. Reach out to our team here at Logic or even Tuxera. We'd be happy to work with you and even set up a private session with your team to go through something like that.
Okay. Thank you very much, Thom, for the interesting presentation. I hope it has provided some useful insights to the people attending this talk today. So now let's check if we have some questions in the chat box. So earlier in the talk, I asked if you could share your experiences on measures that you have in place in the case of a power loss. You may also unmute your mic and simply comment or ask a question if you want.
So maybe let's go to some questions that were asked in the chat for both of you. Picking out one or two. There's one that refers back to the copy and write scenario. Which the question is, doesn't the copy part actually increase the flash memory wear?
Sure, because what you're doing is copying the data to a new write page, but really that's the only way you can modify it. In reality, you're going to copy it to a memory buffer, and you're going to make modifications at that level and then commit it to the media when you're ready. The file system does a great job of keeping that data in the memory buffer as long as possible, but when it needs to be on the media, that reliable data integrity puts it on the media. So it's a great balancing act there.
Okay, thank you, Thom. Then another one that goes more back to provisions on hardware, where the question is, at least theoretically, there should be power backups for maximum availability. So why is power interruption a problem?
It really depends on your design. And yes, there are some designs do have great power backup. Some even though they have power backup, the only way they shut down is a not clean shutdown. It's just a flat power off. File systems don't like that. When we've got a lot of data sitting in a memory buffer, it needs to be committed. We're expecting it to be committed. Any file system. That's true of ext4 as well, where the journal data gets committed immediately, but the data which is sitting in the buffers might be in those buffers for 30 seconds, 40 seconds, 50 seconds. I mean, quite a long time. And if you don't shut it down cleanly, it doesn't really matter whether there's a battery backup or not. If things are done properly, the battery backup can actually work quite well here, but there's other situations too, like the system crash that I mentioned. When the system crashes, it tends to stop writing things, and you end up with whatever state it was. So.
Okay, thank you, Thom. There are some more questions regarding the security, which I believe are very interesting, but go a little bit beyond the scope of today's session. Also, looking at the time. So probably it's best to reach out to the team to have a private session on these.
Okay, that sounds good. Thank you. I've got on screen here the remaining roundtables for the week. Tomorrow, adapting to embedded GUIs, which looks really interesting, and Friday, product development on steroids, which is obviously the best way. So
yeah. So if you haven't signed up for one of our sessions, feel free to do so. And if you happen to have any questions after this session or want to receive more information, you can contact us via the Embedded World platform or have a look at our website. Once again, thank you, Thom, and thank you for your time and for being with us, and hope to speak to you soon.
Yeah, thanks, Gevorg. Really appreciate it.